So the next item is really very much about, it was announced actually at last year's Fall Summit. We were talking, Dean was giving his traditional key closing lecture. It was really nice, and John Elder was in the audience. And at the end, I had the pleasure of moderating Dean. I essentially asked John, who was sitting there very innocently and was probably trying to remain anonymous. I said, how about we have you two guys on stage next year and we'll do a battle of the dinosaurs? That's not happening. But so we thought we'll do a sort of a dinosaur fireside chat, and it's going to be something like what you see here, right? By the way, I'm the green, cute little one. The real dinosaurs are the other two. And it's going to be more for friendly conversation. This is not about controversy at any price, but really getting insights from two people who really have been around, doing data science forever. I mean, Dean Abbott, everybody knows, he has been instrumental, has written books and has been giving talks left and right. John Elder with Elder Research, this is the best data science consulting firm in the US, there's no doubt about it. And both of them, this is also very unique, they're good friends. They try to avoid to be at the same events, not to compete with each other. So this is a pretty unique opportunity to have both of them at the same time in a virtual, at least in a virtual room. Welcome. Let's see if this works. They should be popping up on screen. There they are. There's a dinosaur.
But you know, the good thing about dinosaurs is eventually, even if they're not useful for anything at the time, eventually they will be useful after they're deep in the ground.
But they'll all be coming back. Oh man, he's taking off his head. That cannot be good.
This is like the Masked Singer.
Very nice. Thanks for joining us today and playing along. I mean, it would have been probably even more fun if we could have had drinks before and afterwards in Austin live, but we'll do that next year or whenever we're allowed to travel again. But it's great to have you, virtually at least. And I guess the idea was really just get your take on a couple of topics, and we talked about that last week briefly. What we could, there's tons of stuff that we could be talking about. We could do this forever. I'm pretty sure I'd just be sitting here listening to you guys for 3 hours nonstop and enjoy it. But we have about half an hour. We thought we'll kind of kick it off with something around change management and what you guys have seen in the real world when reality changes, something I mentioned very early on during my intro, but reality changes like in March and April, and what people do to actually keep their models updated.
Yes, excellent. Well, I'll start off. I think all of us are fascinated by the technical problem initially. Science, you eventually realize that the real hazard to getting your work implemented is more the soft issues, and you gain a lot of respect for the challenge of change management, of actually getting what I call, the carbon-based life forms to actually use your models. And so the issues of trust and of getting people to trust you and trust your models turn out to be far more important and more of a risk factor than the technological issues, which almost always can be solved.
Yeah, and one of the issues that we see, especially like COVID, is one of the examples that my company, SmarterHQ, which just merged with Wunderkind, so now I'm Wunderkind. But one of the issues is like in COVID, people's behavior is changing. Machine learning algorithms assume consistency between the past and the future. And that's why we do what we do. We look at historic data and we find those principles, those patterns, and we apply them to the future. When things change, of course, it's a big problem because then the models won't be accurate. So one of the questions is always, how do you figure that out when that's happening? And I've been asked that question a lot. What has COVID meant to all of our clients, our 100+ clients? And something that's hard to uncover. I mean, of course, you can look at individual columns in the data to see when the statistical properties of an individual measurement is changing, and that helps. But sometimes it's more subtle than that. Sometimes it's multidimensional. Sometimes it's just temporal. So one of the things that I like to do in this regard is, even if you don't know and it's hard to uncover, even from looking at model scores, sometimes I'll actually build a model to predict the time period that the data is a part of. Like you create a historic data set labeled 1 and the new data is labeled 0 or vice versa. And if you can separate out the a year ago from data from the new data with logistic regression, then there's something fundamental in the data that's different between what you saw in the past and what you're seeing now. And so I was doing a lot of that kind of before, after multidimensional modeling to try to uncover what changes were occurring in the data.
So if I can jump back in, that's a great example of an interesting technical problem. So
Yeah.
that's Dean's doing a great example of saying, here's a way to solve a really interesting technical problem, which is you had a systemic change in the underlying data. And what I was talking about is a non-technical problem, is you have solved the problem, you've delivered a solution. If they just implement it, everything's going to be fine, and they don't implement it. And by the way, that happens a majority of the time. A majority of the time in our industry, when technical people create a solution that will work if they implement it, the business people don't implement it. Now, with our 25 years of experience in consulting, we get 90% implementation, but the industry average is more like 30% or less. So why is that? And that is because of change management, which is people fear change. People don't want to change the way they make decisions. And so the problem isn't technical, not even a sophisticated problem like Dean's talking about, where the system isn't stable and underneath it all. The problem is psychological. And so there's a lot of ways to address that. The main thing is getting allies working with you from the very beginning and getting that trust involved. But that is the main issue to getting.
So John, I agree with you. Most projects fail at a different level. That technically they're successful, but they fail because of either not syncing up the objectives that the management or the decision makers really want. They can't articulate it properly. The data science team solves fantastically, but they solve the wrong problem. Or sometimes it's an implementations issue. The DevOps engineers, the SREs, don't know how to deploy it, or there's a political barrier to deploying it because, I mean, look, I've had this happen to me many times where the analysts are such an annoyance because we're asking for data to be sucked in that they've not done before. So we're just adding more work for them in spite of what the benefit that there'll be to the business. So, and those to me are two different parts of this problem where the solutions are very different. But in either case, one of the things that we as the analysts need to do is make friends with as many different parts of the organization as possible. And I usually call setting up the problem in this regard the three-legged stool of successful analytics, where you need all three pieces in place at the very beginning of a project to sync up what the domain experts and the project managers, their view of what we're trying to accomplish as a business. The analysts, us, the elder research and what I do to make sure we understand the problem and are connecting, but also the IT and the infrastructure and the DevOps side to make sure they understand what is required of them. And
they usually see us as a huge annoyance, like you said. We're just adding, we're number 11 on their top 10 list of things to do. We're just adding work to their already busy day.
Exactly.
How often do you actually see deployed data science projects being so handcrafted and evolved over the years that it's almost impossible to retrain? So my example here is Google Maps, right? After the shutdown was lifted in Germany, traffic predictions going from Constance to Berlin, I literally drove, were totally out of whack, right? Because Google Maps still had all sorts of little site models built in and little site constraints that, okay, it's a Monday, it's right after a holiday, it's going to be a disaster. And there was nothing, right? There were a couple of trucks, so I was in Berlin, right? And the funny thing is my Volkswagen stupid old navigation system that just looks at the map was way more accurate than Google Maps. It took Google Maps months to get back there. They had to revisit all of these assumptions that were kind of hand-coded in the model somewhere.
Yeah, interesting point. And that's much more like Dean was talking about, where it was heavily dependent on the training data that was used to a certain stability of a system, and that system was thrown completely out of whack. And so it was essentially overtrained to what had been a stable system and now wasn't.
Yeah.
Yes.
And a lot of it's not even necessarily only the data, also the assumption on how you build the model, right? All of the meta stuff around it, kind of where you're injecting expert knowledge assumptions about that matters, this doesn't matter. Yeah.
So let me try to bridge the technical and the softer skills together. it's extraordinarily difficult, especially when your organization is embarking on new analytics initiatives. It's extraordinarily difficult to define it up front, like to get all your ducks in a row and go and then be successful. I almost never see that happens. Almost always what happens in my most successful engagements is you get trust and buy-in up front. You try to solve the problem, and then you're wrong about like half of the assumptions, and you're wrong about so many things. So but my background is in applied math and control systems, and closing the loop is so important. So getting feedback from the stakeholders, the data people, the analysts on a continual basis throughout the project is so critical, because then you uncover things you have to adjust and adapt in the middle of the project. And if you don't do that, then 6 months go by, and it's like the open loop system that diverges more and more until there's no way to get back, like what Google found.
Yes, what Dina said, one of the hardest things I have to teach my employees in the art of consulting is you have to talk to people much more often than you want to.
Yes. And it's obvious to you, it's not obvious to putting on the arrogant data science hat for a moment, where we think, oh, they just don't get it. They don't understand statistics. They don't understand machine learning. It's true, they don't. But you probably don't understand business and all of the inputs they're getting, the stressors they have, like they do either. So we have to kind of lower the wall, be more, John, we talk about this a lot, be humble, ask a lot of questions, let them explain things in their language, and then try to translate the language so that you can be on board with the same ideas.
Right. When I said talk, I meant talk and listen. Yes.
Yes.
Actually having a conversation. Yeah, absolutely. That's interesting. So this is really about putting models in production and how you deal with change. What are the kind of trends that you see around new techniques being used? Right now, everybody talks about deep something, deep X, deep, but the hype is already cooling down a little bit. Is there some stuff? I mean, interpretability seems to be one thing, people really trying to understand decisions that seems to be popping up more often. What else is kind of new or on the horizon?
Yeah, I'll just say, just quickly from a technical perspective, I think you're right. I mean, deep learning obviously has sucked a lot of the oxygen out of the room, at least at the advanced end, or the more leading edge or bleeding edge end, which is kind of funny, because for the dinosaurs in the room, and Michael, you are one of the dinosaurs, you have to acknowledge. Seeing the stuff going on with deep learning, it feels so early 1990s, doesn't it? Because it's a lot of the same assumptions, the same optimism and hype we saw, decades ago. But the other part that's interesting to me, from a technical perspective, is things like XGBoost and ensembles of trees have become much more mainstream. And I'm seeing more people wanting to start there. Now, the danger with all of this is the vast majority of problems we're trying to solve in analytics really don't require a lot of sophistication. The data is not that complicated. The data is usually not that big. I mean, there's plenty of problems like that, but the vast majority, the center of the density of all the problems are simpler. And I just gave a talk recently on this, talking about this, simplicity is better. That's the Occam's razor approach. If you can get essentially the same accuracy out of an XGBoost or a k-nearest neighbor, look, please choose k-nearest neighbor. It's easier to build, easier to maintain, less prone to those dark problems that are way under the hood and hard to diagnose. So I think that's one of the things we've got to kind of pull back all the new budding data scientists who are super excited about the advanced algorithms, pull them back and at least start simple.
I'm kind of known for being an enemy of interpretability, because most of the problems that I work with, accuracy, provable accuracy, out of sample accuracy is really the important thing. But clients love to have some interpretability, and we often have to see what we can do with different levels of models. Maybe start with a simple linear regression type model with really good variable construction, feature construction can go a long way. And that also helps with that comfort and understanding and trust. And what you can do is you get something that works better than what they're doing now, and then you can earn the right to do more and more complex, more accurate models as they get comfortable with it and accept it, whereas they wouldn't take a black box model if you started there. And so see if you need that complexity, see if you earn it. And people sometimes want to have a model that they can get at least some interpretable insight out of. And sometimes you have to build a family of models to give them some benefits of both worlds.
Yeah, and I like to me, the 80-20 rule of innovative predictive modeling is the models 80% of the time do super obvious things that when your stakeholders look at it, they may even roll their eyes and say, I didn't need some fancy algorithm to tell me that. I know that. But there's the 10 to 20% of stuff. And the ideal there is when you start explaining to them, interpreting the models, explaining what the models are doing, even if it's a black box or a gray box kind of algorithm. Like I always like your gray box description, John. But those kind of algorithms, then to say, well, what this subset is saying is this, and they kind of squinch their eyes a little bit and they go, yeah, I never thought of it that way before, but that's really true too. Now, you have to be careful because people are incredible pattern recognition engines, and they'll find patterns places where there really are no patterns. But if you can give them confidence, give the stakeholders confidence, even if, just by showing what the more advanced things the algorithms are doing, it can help with that level of confidence after you've proved that all of the obvious things are being found by the algorithms. If it doesn't find the obvious stuff, they're never going to believe anything it does, even if it will make money for them and be successful.
Yeah, that one I totally agree with. I mean, there's a bit of trust building, and then you can come up with the surprising insights where they say, this is weird, let's try to understand what's going on. Yes, absolutely. Yeah. So what's your take on, I mean, that's something I have very mixed feelings about, this idea of building extremely complex models, deep neural networks on data, highly complex stuff, and then in order to explain them, you train a super simple model that's like a decision tree or a couple of rules in them and say, that's the explanation, that's what the deep neural network does. And I'm scratching my head, it's like, why didn't you use the rules in the first place if that's what it does?
Yes, no, there's really it's very interesting. There is a use for that. There is a purpose for that because have a very cloudy space. There are some modeling techniques that will do a good job of finding a compromise surface through that space. And then you can build a wireframe version of that model, and then you can use a simple, say a decision tree or something, to fit that wireframe, and it won't overfit because it's constrained by this smooth surface, not a noisy surface. So if you use a decision tree to fit that noisy surface, it would overfit. It would give you a very rough. But if you're using a decision tree to fit that compromised smooth surface, it won't be overfit. So that intermediate step, you've said, I'm gonna trust my smoothing to this deep neural net or this huge ensemble or something that can do a better job of generalizing this high dimensional, noisy, sparse space. Yeah. And then you can turn loose a lower dimensional interpretable method without fear of overfit. That's the secret. That's the key, because there's no fear of overfit now because you're fitting a smooth surface rather than a noisy, sparse surface. So that is a cool trick. It's just a question of then does that really make it interpretable now that you have something that's piecewise linear or piecewise constant or something like that. Mm-hmm. I think locally it is, like fraud, like in a credit scoring problem, for instance, you don't need a globally interpretable model. You just need to interpret it at one point. What are the features that are most relevant to this particular person's being rejected for credit? So at that point, its slope is most affected by how many credit cards they have open, what their largest balance is, that sort of thing. And you can explain to that person what most affected their credit score. And so the locally linearly interpretable, that's a neat feature. You don't have to have the whole thing be interpretable.
Yeah. Well, there I agree. I mean, the difference between local and global, that certainly makes sense, looking sort of just the vicinity of that current data point. But
Yeah.
the other one, I mean, it's almost like saying you build a gradient boosted model and you take the first one or two trees, and that's the explanation of what the overall thing does. Right?
Which is
Yeah,
okay. Which is okay. And at a high level, I mean, it's at a simplistic level, it does explain the gist. And sometimes that's all you're trying to get across is the gist. And I've gotten models through banks, through Revenue Canada, that were more complex models by doing that approach you're just describing, Michael, building a simple model. The key is you predict the model outputs. You don't predict the original target variable, you predict the model outputs because you're trying to build a simpler model to explain the more complex model, just to make sure the audience is clear in that. But I did that and they said, okay, I get it, I believe it now. That's at the kind of the broad, simplistic macro level. At the micro level, it's also very useful to do like what John's describing, almost like a nearest neighbor approach to show prototypes. This is how this kind of pattern is being classified by this model. And that is really helpful as well. Just one shout out to, I love something I use in Knime regularly when I'm building random forests in Knime that I've not seen in any other tool, is you give that report that shows which variables were selected in the top level, the second level, the third level deep in the trees, in the random forest set of trees. And that gives you a good kind of gist of what variables are more important there as well. Very useful, and I haven't seen it anywhere else. So just if anyone's out there building random forest and Knime, definitely use that report to interpret your models.
And let me point out here, that's a great point. And let me point out here too, some research has shown that if users have a chance to play with a model, for these inputs, it gets this output, for these inputs, it gets this output, that's as good as interpretability in terms of their acceptance of a model.
For the local stuff, yeah.
I
So-
believe that.
So
Can
if you had-
after we're done, I'd like to read that.
So let's push that a little bit further, right? In the European Commission, they're currently discussing that AI models, we all know it's all machine learning, or any type of model. They're going to have kind of 5 different security classes, call it what you want, right? So if it's just predicting churn of customers, who cares if it always works and sometimes fails, right? But if it's controlling a nuclear power plant, then that's level 5, right? If something goes wrong, not a good idea. And then the demand is actually to be able to formally verify that the model doesn't do what it's not supposed to do. And I'm thinking if you go that far, I don't think you do machine learning anymore. I mean, because then it needs to be such a simple model in the end that you can verify all sorts of these side constraints that it's an extremely simple model at the very least.
Unless you could, do like a grid search, or like populate all the possible values of the inputs and say, in this cube, we know exactly what it's going to say at all times,
Like
And that's really what a scorecard does, essentially, is create that kind of grid. And I that's true. I share your pain a little bit on that, Michael, because it if you have to simplify so much so that you can tell exactly what the model is doing, then you'll lose the complexity of the model, because it is the more advanced models have to be more complex than what you could just describe in a simple rule or sentence, or else we wouldn't be having these PhDs generate all kinds of dissertations about all these sophisticated things. I mean, there's no fun for PhDs if you can't have something new that's sophisticated that only like 10 people in the world can understand, right? But I think there's a way, like John said, the only way through that, to thread that needle, is with the data. So for this kind of pattern, what does the model do? And to be able to characterize that and demonstrate, and I don't know if this is possible, I'm just thinking kind of outside the box, and to demonstrate that the sensitivities, the changes, small changes in the inputs, do not produce significant changes in the predictions, so that you're not susceptible to some, like what we used to see, especially with deep learning and images, where imperceptible differences in the images would cause classification error, because they're just so complex and they're so brittle that small changes really can produce large changes in the predictions.
That's True. I mean, it kind of reminds me of hardware verification, right? I mean, the way they're doing chip verification, even circuit layout verification, really, the circuit that it does what it does is by testing, right? Just trying tons of things. And really formal verification of circuits is probably possible these days up to an old Apple II, maybe, right? They can do that now. But the modern processors, there's just no way to really do a formal proof that it works, so they test the hell out of it. Maybe that's really the answer to it. Yeah, that's a good point.
I think the European Union just needs to, formally enforce input shuffling. So.
Yeah. I mean, that's sort of these techniques that you try to get the data scientists that you educate to start using to just sanity check if what they're doing is not, anyway, it's kind of funny to see how a lot of papers get retracted these days from biomedical literature where they ran amazing, cool results. There's a very famous cancer test. They had to withdraw it because they realized they were just overfitting the hell on the data, right? All of the conclusions were nonsense. And this is really hard.
Well, you've really hit on a key theme that I've tried to speak on every opportunity I get, is that the reproducibility problem in science as a whole, and in AI in particular, actually has a problem. Only 15% of artificial intelligence papers share their code, and even very prominent AI work from Google and Apple and so forth is criticized by others as being impossible to replicate. But a huge number of papers in all fields, medicine, chemistry, physics, more than half of all published papers are believed to be unreplicatable. So it's a real crisis in science, and most of it is due to repeated experiments and using old statistical tests that were designed for a single experiment to calculate the significance of what are really repeated experiments. Target shuffling is the answer to that. And
there's a note for that in Knime as well, don't worry. We should have really called that the John Elder note, but then people might have not found it. No, that's actually true. At least when you read biochemistry papers, at least there's a section in there that tries to tell you how to reproduce, and then you read these algorithmic machine learning papers, they don't even care about that. And I totally agree. I mean, you get a really crappy library that does something similar to the paper, but it doesn't really allow you to reproduce. Yeah, that's certainly a problem. But anyway, that's probably going a little bit too far off. One other topic that's always on my mind is when I've done a little bit more machine learning theory during my PhD, and when I have conversations with people about saying, but you need to build models that don't discriminate, then I say, well, the idea of the model is to discriminate. Usually, you're trying to discriminate good from bad customers, right? And then you get into this
discriminate is, of course, an overloaded word.
Exactly.
It means something in the general society that's a bad thing. It means something very good in the machine learning world. Yeah. That you're making a distinction between two things, and you're trying to do something very good. But yes, this is a political correctness. I was on a panel to advise a government agency, and there were a number of people on that panel. And if you're bringing up the equity or racial discrimination or gender discrimination, there were people on the panel that were urging the government to modify models for political reasons to make up for past injustices. So no matter what the data said or no matter what the right answer was, they wanted them to, as a matter of law and policy, modify the models to get the right answer so that the right communities would get more rewards. And this was just horrifying to me. I couldn't believe that this was being suggested. And I was, as far as I know, the only one arguing against that in the advice. So
that's almost like the opposite of trying to make your model less discriminating.
Exactly. I mean, my argument was we need to make models as accurate as possible to what the data said. And of course, if the data has any bias in it, which it could, because the data might be based on biased judgments by humans in the past, that can be discerned and corrected. But we certainly don't want to bias the models further in any direction. We want the models, our job as data scientists is to reflect truth. And then, it's another stage to decide what to do with that politically, but it is our job to discover the truth.
Yeah, and this is one of the few areas that in the Twitter sphere and LinkedIn, I push back, because when I read about machine learning bias or AI bias in the algorithms, the bias is not in the algorithms. Math really does not care. It's the bias is in the data.
Yeah.
And we have to be aware of it when we're building models. And Phil has done such a great job at prior Knime summits talking about this issue, how to detect biased data to make sure that we're not violating whether statutes or getting, like you're describing, John. We're trying to uncover the truth of what's going on. And if the data is biased, then of course we're not. We're getting a biased view of what is actually happening. And that's almost always the case. Our data is almost never a complete random sample or complete representation. But the models themselves have nothing to do with that. The models just find what's there, and then we do the best we can. Like you're saying, John, tell the truth, have the model figure out the truth, and then decide what to do with that information. And you could use it in part or in whole to compensate for things that are not represented in the data. I mean, that's a different judgment process. But I really want to push back, like you did, John, against trying to change the algorithms with priors, to put it in a more technical context, with priors that we assume are there that we can't justify from the data, and just to achieve the outcome, or to force the models to do something. That's kind of like what we would always complain about when people would beat the data till it confesses, kind of that kind of approach. And that's what we're doing with the models in this context, which I think is a dangerous thing to do.
Do you think is it always a data bias, or is there sometimes it's probably also a data bias, right? You have something that has been done incorrectly or discriminatory in the past.
Yeah,
and that's what you learn from
absolutely,
the data.
because
good point.
You're collecting what data you can, and sometimes you can't collect the fully representative data because of if there's bias in the system in the past, if there's whatever that bias might be. So the models themselves, though, they just don't know any better. They believe, the way I usually say, models don't have common sense. Algorithms don't have common sense. They believe everything you tell them. And the only thing you tell them, the absolute only thing you tell them, is what's in the data. So we as humans look at that data and we may see a value. We say, that's garbage. I know it because I know stuff outside of this one limited environment. But that's all the algorithms have. So we have to work on the data to make the data represent.
All they know about the world is encapsulated in that data, and it's our job to curate that data so that we are telling them true things about the world. So if we tell them that data is very important, we have a responsibility, but to and this is in other ways too. For instance, you have clients that want certain results out of their data. They have certain ideas about where fraud is, or where profitability is, or where stores should be opened, or whatever. And there's a lot of pressure to get certain results. And it's our job as data scientists not to get those results because of the pressure, but to get the results that's really in the data.
That's right. I know I hear that all the time at SmarterHQ, or some of our clients, they want to be data driven, because data driven is like a real cool thing now. In a way that it didn't used to be. But they want to be data-driven as long as the data says this, right?
Yeah.
And once the data disagrees with you, the data's not right.
So we have to find that result, otherwise the boss isn't happy.
That's right.
Yeah, I've heard that too. Very cool. So we cannot have a little panel discussion without saying the A word, right? And you have said it left and right. So artificial intelligence. You want to have how about some concluding remarks of the future of artificial intelligence? Is it going to rescue humanity?
No, but it's not going to destroy us either. So I have a very humble view of artificial intelligence, whether they want to have that of themselves or not. I was on a panel 3 years ago in Dublin, and on that panel, Barry O'Sullivan, the head of an AI consortium in Europe, was there with me. And he called AI, this is the first time I've ever heard this from the head of an AI group, He said AI is just good engineering. And I looked at him with astonishment. I am in complete agreement. So he and I were the only two on the panel when asked the question, is the great convergence going to happen? Is general artificial intelligence going to exceed that of humans? And he and I said, absolutely not, impossible. And the others on the panel looked at us with complete astonishment. They assumed it was inevitable and was going to happen within, 10 or 15 years at the most. And pretty much if you'd asked we pretty much asked the audience there, and you could have done about a very accurate decision tree that basically everyone under 40 agreed with the others on the panel that yes, it was inevitable. And most of everybody over that age agreed with us old fogies that no, it's not going to happen. So it was a very interesting phenomenon. I don't know how this audience would vote on that or not, but I've worked a long time trying to make machines smarter. And I'm telling you, they're fast, they're loyal, they're obedient. They're like a really good German Shepherd dog just sitting there waiting, eager for you to throw the ball. And they will go get that ball, but they know nothing about the world other than the data you show them. I have no common sense. They're a great assistant, but they're really dim-witted. And I just see no hope for them to get better. They're faster and, more helpful all the time, but you gotta tell them a very, very specific task.
Yeah, no, I agree with that. Maybe the old guys are just stubborn, but anyway. Dean.
Let me show one thing, Michael, if we can, because I showed this slide like this a couple years ago at a Knime summit.
Okay, we can try. We'll see what happens now.
I'm just going to show you three quotes.
Okay,
and only three quotes. There are many more quotes.
That doesn't quite work. Can we do full screen, man? Just a second. We need to make this full screen. You did not. You're not actually scheduled to share any slides here.
Oh, that's okay.
But we'll figure this out. Yeah, exactly. You're not authorized to do that.
I'll just read a couple of them quickly, and then people can have them.
Sounds
this is because these go back to the 50s and 60s. So in the 60s, in 1961, Marvin Minsky said, "Within our lifetime, machines may surpass us in general intelligence." Or in 1970, in 3 to 8 years, we'll have a machine that has the general intelligence of a human being. So these kinds of ideas have been around for a long time. And Jeff Hinton just recently had a paper out where he said deep learning is going to be able to do everything. One reason why I'm in full agreement with John.
And these guys were all as prominent as Hinton is now. Yeah.
Yes. Oh, yeah. Marvin Minsky was, and super smart guys. I love the technical work they do. But here, my concern about it is just like what John was saying, is that too much stock is placed in the algorithms. Let me give you one reason why I think AI, deep learning in particular, will not solve all these problems that we say they're supposed to solve. When we build a predictive model, we're trying to take one column of data, which is the target variable, and try to find associations between the inputs and the target variable. How do we judge how well we are predicting that outcome? We're judging that assessment with one number, and that number could be something as simple as the root mean squared error. Why in the world would we ever believe, ever, in anything that's rational, that root mean squared error is representative in any significant way in how good something is? We don't do that ever in our own lives. The model that we have internally in our brains about what's good or not is very complex, which is why optimization methods are so powerful and so flexible. Simulated annealing or variational calculus. There's a target and there are constraints. It's a multidimensional score function that we don't get with deep learning. Will we get better with deep learning? Hopefully so, but we have to at least get that far to have something that's more sophisticated in how we judge what a good representation is before we land in something that's good here. I'll get off my soapbox now.
And then it's still only good engineering. I like that quote. That's a very good one. Awesome. Thank you very much. That was a lot of fun. As I said, I can do that a lot longer, but we have another agenda item coming up in 15 minutes. Thanks a lot for playing along. It was a pleasure, and hopefully we can do a repeat of this one on a sofa in a year from now in Austin with a beer in our hand or something. Until then, thank you.
Thank you, Michael. Good to see you, Dean.
Thank you. Good to see you, John. Thank you, Michael.
There we go. Bye.